Hey, I'm continuing with part 2 for geometric series. So we're still day 2 of our unit of sequence and series. I just covered arithmetic series in the previous video. Now I'm continuing with geometric series. Again, just a reminder, series is when the numbers of a sequence are being added together. And we could have finite series where we're adding certain number of terms, like 10, 15, 20, 100. Or we could have infinite series where we're trying to add infinite number of terms of the sequence. Now with geometric series, there's just one formula for the sum. And to be able to utilize this formula, we need the first term of the sequence, and we need to know the common ratio. And then n obviously represents the nth term, and this is the sum of all those n terms. There are, I think, 4 or 5 examples, and they're all different and very important examples, 5 different types. Let's continue with them. So some of them are super basic, like this one says find the sum of the first 5 terms of this sequence. So clearly n is 5 here, and the ratio, r, common ratio, is half right there, which means I'm trying to find S5, formula being a1 times 1 minus r to the power of n, 1 minus r. We have all the information given. Not directly though. So the first term, sum of first 5 terms, I need to first know the first term. Well, I don't know the first term, but I can simply plug in 1 for n in this equation. That gives me half raised to the power of, my bad. I already wrote half to the power of 1, which is half. So the first term is half, 1 minus the ratio, which is also half. N is 5. So instead of raising 1 to the power of 5 and 2 also, I'm just going to raise 2 to the power of 5, because 1 to the power of 5 is just 1. And then half here. From here, we just need to be able to take care of this setup that I just wrote. Now, this can be plugged in directly. This part can directly be plugged into the calculator, or you can break it up a little bit. Up to you. This is 1 minus 1 over 32. That's half. That's 31 over 32 over half. And when you simplify this, you end up with half times 31 over 16, which is 31 over 32. So the sum of the first 5 terms add up to 31 over 32, which is almost 1. This is actually a convergent series. We'll talk about that a little bit later. And I continue. Sum of the first 10 terms. So again, very straightforward, sum of 10 terms. Do I know the first term? It's like, yes, I do. Do I know the ratio? Well, we're multiplying by 5 times 5 times 5. So the ratio is 5 raised to the power of n, not n, but 10, over 1 minus 5. That leaves me with 4 times... I need to grab the calculator again. Okay. 5 to the power of 10, it's 9765625. That leaves us with 2 negatives and 9765624. And that is the sum of the first 10 terms. Then next question here, which is example 8. Also a geometric series. As you can see, we're multiplying by 1/5 every time. So r is 1/5. First term I is available. Let's see what the question's asking. It's asking to write explicit form of this sequence. This, if you notice, is only focused on the sequence. It's from the last unit, lesson, from the last lesson. If you look at B though, this one's asking for the sum of the first 6 terms. Then this is today's lesson, which is this sum or the series. Now, because this is geometric and they're asking for explicit, on your formula sheets, you can find the formula to be a1 times r raised to the power of n minus 1. So nth formula is 625 times 1/5 raised to the power of n minus 1. And they ask for generic formula for geometric sequence. And I wrote that formula. They didn't ask for recursive, so I wrote explicit. Now that we have the formula handy, finding the sum of the first 6 terms, like I said, the formula for sum is the same that we've been using. a1 times 1 minus rn, 1 minus r. Do we know the first term? 625 1 minus 1/5 to the power of 6 over 1 minus 1/5. This can be plugged in straight into the calculator. If you want to break it up, I'll break it up a little bit. 5625 over 4/5, which is 15624 over 5, and then times 5 divided by 4 times 625. That should be 781.2. That's the sum of the first 6 terms. I mean, 4 terms are already written, 625, 125, 25, 5. So the next 2 will be 5 and 1/5. So basically, when all these are added together, we get 781.2. Alrighty, moving on. This is also another type of question saying how many terms, how many of these terms do we need for the sum to equal 5461? It's a geometric series, so again, the same formula. A1, 1 minus r, and O1 minus r. N is what we're trying to find. All other pieces of information are given. Sum is given. I know the first term. I know r over 1 minus r. That gets me, I'm going to go this way, over -3, multiply both sides by -3, which is that. Okay, continue solving it. 4 to the n equals 1 plus 16383. 16384. We're trying to find n, so we'll have to get logs into consideration to be able to get that n at the normal level. And once you plug this in the calculator, n turns out to be 7, which means the sum of 7 terms will add up to 5461. The 4 are already provided, like if I do 6, 7, 8, add them up, it should work out. So that's that. Then another topic here is trying to figure out if a series is convergent or a divergent series. Jumping straight to convergent and divergent, this is an example of a convergent series. What that means is that the sum, now clearly this is sum, so the sum of the numbers of this series, which would be like, first would be half, 1/4, 1/8, 1/16, plus 132, and so on and so forth. It's interesting how all these will start to add to a number that's going to approach 1. It's going to get closer and closer to 1. If you try and tie it up with exponential, this is exponential decay, which means it kind of goes like that. If you recall, there were also asymptotes associated with it. So the number that we're adding every time, it's getting smaller and smaller, which restricts the sum from going over a certain number. In this case, it wouldn't go over 1. Look at the other one though, like this is an exponential growth type, which means the numbers of these series just get bigger and bigger. First one will be 20, second, basically I'm trying to plug like numbers in. So 4 times 25, which is 100. See if I can, no, I can't do that. 5 to 10, whatever, that's going to be big numbers. And these numbers are progressively increasing in this series. So when we try and add them, we're really not going to approach a certain number. In fact, it's going to approach infinity because the sum is just going to get bigger and bigger. If the sum gets larger and larger, such series are called divergent series. So we cannot really find the sum. But with convergent series, we can actually find the sum. And the formula to that is this right here. One more time, if a series is convergent, then we can find its sum using this formula. If a series is divergent, we're not going to find its sum. So here's an example. They're saying, hey, first determine what kind of series is this. Like, look at that. Because the R value is less than 1, which means the numbers are progressively getting smaller, this is a convergent series. Do I know R? Like I said, yes, I do know R. R is 2/3. Do I know A, which is the first term? So first term, you plug in 1 here, and you calculate the first term to be equal to 2. Now that I know it's convergent series, that means I should be able to find the number the sum is approaching using this formula. Sum is equal to first term over 1 minus R. First term is 2. Keep, change, flip, and 6. Which means if I list the numbers of this series, 2, first will be 2, second will be 4/3, third will be 8 over 9, 16 over 27. Oh, I should have done plus in between, plus. As you keep adding this sum is just going to approach, actually not even approximately, it's going to approach 6. The other one, on the other hand, because this R value was 6, which is much greater than 1, when R is greater than 1, then this series has to be divergent series. And because it's divergent series, we cannot find the sum, so we leave it there. And not only this, it also needs to be less than -1. So here's the criteria for convergent. I know I'm kind of going fast, a little bit faster here, but the idea was for you to be able to watch this video since I have to step out. And the last part here is very interesting. If you're not minding this so far, they're saying, hey, what does this equal as a fraction? Like what over what? Like this can simply be calculated on the calculator. But the idea is, I want to show you how series plays a role in this. From what you have known since you were little, that, hey, this is 1/3. The fractional value of 0.333 repeating is 1/3. Similarly, you've also known fractional value of 0.666 repeating is 2/3. So it's like, what's the fractional value of this? What's the fractional value of this? That's the question. Oops, there. I'm going to erase that. Okay. Here's a perspective on this, because this is basically 0.2222222 dot 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 dot. Can I not break it up and rewrite this as this? And so on and so forth. Notice this has turned into a series. Not only is it series, it's like, now determine what kind of series is it, arithmetic or geometric. It is geometric. I didn't mean to put a 1, but that's 0, 0, plus, so on and so forth. It's a geometric series. Not only is it geometric, it's also convergent, because I could write the formula of this as, because we're multiplying by 1/10 every time, 1/10 and -1. This could be the formula for this. So not only is it geometric series, it's also the convergent type, which means I should be able to find the sum of all these put together using that same formula, which was first term over 1 minus R. Well, what's the first term? 2 over 10. What's the ratio? R here for the series is R is 1/10, because we're multiplying by 1/10 every time. So 1/10. That is 210 over 9 over 10. The 10s cancel, 2 9s. Here's the fractional value of this. You can plug this in the calculator, and this is 0.2222 repeating forever. Let's try this one. I hope you like the idea. It's kind of cool. 1 2 1 2. That's what this is, right? Like dot 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 repeating. Let's rewrite it as a sum of some numbers. 2 3 4. Because it's since it's going every other place, we have to add even number of zeros every time, which is 12 over 100. 4 zeros is 12 over 4, 5, 6 there, plus, and so on and so forth. Now you can see this is a geometric series, because we're multiplying. Well, A is what? 12 over 100. And R is 1 over 100. We're multiplying by 1 over 100 every time. And not only that, it's also convergent. Because it's convergent, it's like, okay, let's find the sum using the same formula. 12 over 100 over 1 over minus 100. Over 99 over 100. So that's 12 over 99, which does simplify to 4 over 33. So this, when 4 is divided by 33, basically, it just constantly gets into this repetitive mode. And hence we use series to determine that. Hopefully that made sense, and that takes care of day 2. I know it was a lot and I was going fast, but at least you have something. Ta-da!